Welcome. Today we're going to be talking about fluids, and in particular, we're going to talk about how hyperosmolar fluids contribute to a patient's volume status. What we want to discover, or at least understand, is how much fluid a hyperosmolar solution actually causes a patient to retain. And the reason we want to understand this is because of the following. If you have an isosmolar solution, such as normal saline or lactated ringers, for example, these fluids predominantly follow the axiom of what you see is what you gave. In other words, if you have given, say, 500 cc's of normal saline or lactated ringers, then what the patient sees in their body is 500 cc's of that fluid. It's a one-to-one relationship. If you gave 250 cc's, the patient would see 250 cc's of that fluid. That makes sense, but the what you see is what you gave axiom doesn't hold true when you have a hyperosmolar solution. And so common hyperosmolar solutions include contrast, and then the colloids like albumin and hespan. So, and even blood. We can even throw packed red blood cells in there, PRBCs. What we want to understand is how much volume does a patient actually experience for any given amount of volume of any one of these hyperosmolar solutions. Because the patient may be at a greater risk for developing symptomatic edema if we give a certain amount of volume for any one of these solutions. And the reason that is the case is because of this simple model here. Here we have the intracellular space and we have the extracellular space. And hyperosmolar solutions have a tendency of dragging water out of the cells and into the extracellular space, in particular the vascular space, which is what I've drawn here. And it's that extra fluid, what's represented by this arrow, that could tip a patient over into edema. So let's try to go through a simple calculation to uncover how much fluid a patient actually sees for a given amount of fluid that you give that's hyperosmolar. Alright, so what we're going to do is we're going to start with a patient, and let's just describe who that patient is for a minute. It's a male, and we'll say he's 70 kilograms in weight, and we'll say that his serum osmolarity is about 300, which is in the normal range. 300 osms per kilogram of water, which is the same as a liter of water. And let's calculate how much osms this patient has. What we're going to do is we're going to take this patient and we're going to give this patient a hyperosmolar solution, and that is going to be contrast. And we'll talk about what goes in this box later on. And we want to determine how much volume the patient actually sees for a given amount of volume of contrast. So let's work this out. Let's first determine how many osms this patient actually has. So the osms, the total osms that this patient has is very simply calculated by the serum osmolarity times the total body water. And in that case, we get 300. And because it's a man, we say 50%, so 1/2 of his weight, 70 kilograms. And so we'll get the following number. It's the total number of osms that this patient has. Now, the body compartment is such that 2/3 of the total body water is in the intracellular compartment and 1/3 is in the extracellular compartment. So we can say the same thing about the osms. 2/3 of the osms are in the intracellular compartment, 1/3 is in the extracellular compartment. So let's calculate that. Let's say intracellular compartment, and what we want to know is the volume that's in the intracellular compartment and the osms that are in the intracellular compartment. Okay, so the volume is going to be 2/3 of the total body water. And so that approximately comes out to 23 liters. So I just took the total body water, which is right here, and multiplied it by 2/3. And I'm going to do the same thing, take the total body water, but multiply it by 1/3 to look at the extracellular compartment. And that comes out to 12 liters. Now I'm going to do something very similar with the osms. I'm going to say 2/3 of all the osms are in the intracellular compartment. So that's 2/3 of 10,500. So that's about osms. And then 1/3 is in the extracellular compartment. That's about 3,570 osms. Alright, so let's take this information and move on to the next screen. Okay. Alright, so we have intracellular compartment, which is represented as here, and we have the extracellular compartment, which I'm representing as this. And currently we have the following number of osms in the intracellular compartment: 6,615 divided by 23 liters. And in the extracellular compartment we have 3,005. Let's make this a little bigger so it's easier to read. In the extracellular compartment we have 3,570 osms over 12 liters. Now, if you did this math, you'd realize that the osmolarity here is 300, and the osmolarity here is 300. And that's how it should be. They should be equal osmolarity. Now you add contrast to the patient. And I chose contrast, iodinated contrast, the kind of contrast that you use in a cardiac catheterization or a CAT scan or an intravenous pyelogram for the following reason: because contrast is predominantly all in the extracellular compartment. And we're going to use this feature of contrast in our calculations. So all of contrast is in the extracellular compartment. So how much contrast are we giving? So say we have a standard patient undergoing a cardiac cath, for example, and he gets iodinated contrast, and he gets 200 mLs of it. And the type of contrast that he gets is what we call low osmolarity. Now, low osmolarity is not really lower than serum osmolarity, it's just lower than standard osmolarity. Contrast osmolarity can go anywhere from 600 osms to 1800 osms. So we're going to choose something on the low end. We're going to choose 800 osms. Alright, so he gets 200 mLs of contrast. That's at 800 osms per kilogram of water. So how many osms does he get? So we just do 0.2 liters times 800, and he gets 160 osms. Where do those osms go? All of those osms go into the extracellular compartment because contrast stays in the extracellular compartment. So let's now calculate his new osmolarity. So we've got the intracellular compartment here at an osmolarity of 300 osms per kilogram. And we've got the extracellular compartment here where things have changed. What has changed? We have 3,570 osms to start with, and we added some material from the contrast. And that is about 160 osms, so we're going to label that now as purple. And the volume that we have is the 12 liters that we started with, plus the additional 200 milliliters or 0.2 liters from the contrast. So if you take all of this, what are you going to get? You're going to get an osmolarity that's approximately 306 osms per kilogram. And now that is a problem because you've got 300 osms here, 306 here. They have to be in equilibrium, so something has to give. And in the acute setting, after you administer this contrast load, what happens is that volume exits the intracellular space and enters the extracellular space. And it's this quantity right here in yellow that we want to know. Is this a significant quantity? If so, how much is it? Because it can guide us into stratifying how likely our patient will develop edema, and it may guide us in our therapeutic diuresis of this patient post-contrast administration. So let's figure out how much fluid is going to leave the intracellular compartment, enter the extracellular compartment as a result of giving this much contrast. To do that, we're going to say that the osmolarity of the extracellular space must eventually equal the intracellular space. So what is the osmolarity of the extracellular space? It's 3570 plus the 160 from the contrast. Okay, divide that by the volume. So we've got 12 liters to begin with, plus the 0.2 liters that we got from the contrast. Okay. Now water is going to come in here from the intracellular space, so there's an extra x here. And it's the x that we want to solve for. What's that going to equal? That's going to equal what's in the intracellular space, which is 6,615 osms divided by the total water in the intracellular space, which was about 23 liters, minus what we're going to lose, which is x. These two have to equal each other. Let me clean this up so you don't get confused. It's 6,615 osms. There we go, that's clearer. So let's solve for x. And so I've already done that for you. We don't have to go through the cumbersome calculations. It turns out that x equals 492 mLs. Now let's talk about this briefly. 492 mLs. If you remember, we administered a contrast load of about 200 mLs. So this patient actually received the sum of these two. So the effective volume that this patient received was more than the 200 that you gave. The patient actually received 692 mLs of fluid in the extracellular space. 200 from the contrast and an extra 492, more than 2 times what you gave, is what he pulled out, what contrast has pulled out of the intracellular space to give that patient a total volume of 692. So this is considerable amount of fluid, and that's why we started off this lesson by saying hyperosmolar solutions, when administered, do not follow the what you see is what you gave, because what you gave was 200, what you see is actually 692. And this can help guide you in determining which patients are at risk for developing symptomatic edema and what kind of diuretic strategy you need to execute so that they don't develop edema when they're exposed to what looks like very little hyperosmolar solution. And that's today's lesson. Thank you very much.